Good morning, students. As you know, we have to discuss ammonia chapter. So, ammonia chapter means ammonia gas, which is having formula NH3, which is having a relative atomic mass 17, right? Clear? And electron dot structure of ammonia is also given to you in this diagram, right? Okay, so electron dot structure we will be discussing, and that formula we are also going to discuss. Let's see here. This is the structure. This is the formula of ammonia gas, right? Nitrogen having atomic mass 14, and how many hydrogen? 3 hydrogens are there, right? So they are having atomic mass 1 1 and 1, so total atomic mass will be 17, right? So this is relative molecular mass. 17 is the relative molecular mass of ammonia gas, right? Now we are going to draw what we are going to draw its electron dot structure, right? So nitrogen which is having 5 electrons in the outermost shell, right? Because we have to stabilize outermost shell, because electronic configuration for stabilizing nitrogen is 2 comma 8, right? So like this it will be stable. So it is having 5 electrons in the outermost shell. So these circles I have made for nitrogen for the outermost shell, right? Okay, I will be making it again. Like, see here, nitrogen, 1 electron here, 1 electron here, and 1 electron here. Here one hydrogen is there with, I am showing its electron with the cross, one more hydrogen with the cross, and one more hydrogen with the cross, because so that we can easily locate that whose electron is which electron is of nitrogen and which electron is of hydrogen. So hydrogen outermost shell is to be like this. It contain only one electron, so it will be stable like this, it will be stable like this, and it will be stable like this, right? And nitrogen will be stable like this. So this is the electron dot structure of nitrogen, right? Sorry, ammonia. Clear? It remain one lone pair is remain here. This later on changes into NH4 positive, right? Means I have already told you about coordinate bonding. Clear? Okay, now we'll come to the chapter, right? Occurrence. Ammonia does not occur in free state, right? It generally occur in traces, yeah, only in very small amount, right? Clear? Okay, then in generally it is found in combined state. Combined state, for example, it is found in NH4Cl. So here it is in combined state. It is found in ammonium sulfate also, ammonium chloride also. Hindi name of ammonium chloride is Nausidar, right? Clear? So now we are moving towards the side of your ICSE chemistry 9th class chapter, this ammonia chapter. Ammonia and ammonium compounds are highly soluble in water, so they don't occur as minerals. Means you will not be find these type of ammonium compounds as minerals, because these are generally soluble, right? And they generally form weak bases also, like NH4OH is one of the weak base also, right? Clear? The pungent smell which one encounters near a decaying heap or public toilets, right, that is just due to ammonia. When urea undergoes a bacterial decomposition in the presence of water, then ammonia gas is formed. See, this is the ammonia gas formed when urea undergoes decomposition. This is the formula of urea. Now we are moving towards the form of ammonia, right? Gas is ammonia. It is, you can say it is a dry ammonia gas. Liquid ammonia, when dry ammonia is liquefied by high pressure, it is called liquid ammonia. Means it does not contain water in it, right? Clear? And moment you will open the bottle of liquid ammonia, it again start changing into gaseous ammonia, right? Next is this uh, it is also a laboratory bench reagent, right? And liquid ammonia fortis, it is also called, it is a saturated solution of ammonia in water. Saturated solution is that in which no more solute can be dissolved, right? Like that means highest solubility. It is also called as 880 ammonia, and its relative density is 0.880. It is stored in very tight bottles or kept in cool places, right? Next is how to prepare ammonia. See, many reactions are given here, right? I will be explaining which of the reaction is the best reaction for this. So the reaction which I am going to take, this is the best reaction for laboratory preparation of ammonia gas, right? Clear? I will be explaining why other reactions are not so useful, right? Clear? Means you can use this also, this is also a good reaction, but these two are not so good. Why they are not good? Because NaOH and KOH are deliquescent substances. As they are deliquescent substances, so they absorb water, right, to become saturated solution. So reaction will be failed in these cases. And here calcium hydroxide is a slick lime which is cheap, right, and it easily mix with this ammonium chloride, right? Okay, so let's move to the laboratory preparation. I am going to explain you the direct diagram, right? See that round bottom flask is being taken here and it is in a slanting position. Why there is this is in slanting position? As in the above reaction it is shown here that there is formation of water, so the water formed here should not trickle back into this container, yeah, into this round bottom flask, because if it trickles back then there will be breakage of this round bottom flask. So we require temperature also, so for that burner is there, and on heating it what happen, there is formation of calcium chloride which will remain here. Water and ammonia gas will start moving towards this delivery tube, and a perforated chamber is here, right, where this ammonia gas comes and start moving through the packing of calcium oxide, right, CaO, which is also called as quicklime, right? So this quicklime will absorb water part and will dry it. So you can say here CaO is acting as a drying agent, right? But in the exams generally questions is being asked that why we are not using H2SO4, that is also drying agent, phosphorus pentoxide, that is also drying agent, calcium chloride, that is also drying agent. So the answer is very simple and it is written here: if we use these drying agents then they react with ammonia gas and your reaction defeats, right? You are not able to get ammonia on the other side of the products, right? So they are unsuitable drying agents. Means they may be suitable, like H2SO4 is suitable drying agent for drying of HCl gas, but not suitable for drying ammonia gas, right? Clear? So these are the examples of some drying agents which cannot be used to dry ammonia gas. Now collection of ammonia gas, right? Ammonia gas is collected in inverted gas jars by downward displacement of air, obviously not in a chamber where water is being contained, right? Because ammonia is highly soluble, right? This ammonia gas which is collected in this chamber is highly soluble, understood, right? And higher ratio by weight of the alkali should be used, means its weight should be large and it can be used here, so that ammonium chloride should be mixed with this calcium hydroxide properly. Why we are saying like this? Because ammonium chloride is a substance which is sublimable, so when we heat it, it will sublime and its vapors will be formed and ammonium chloride will be deposited in the inner walls of the container. So it will be a great difficulty, right? Means to get the reaction in a proper way. So we add large amount of alkali in it so that mixing will be proper, right? Calcium, why we are using calcium hydroxide? Because it is cheap, right? Though means other ammonium salts on heating with alkali uh, give NH3, but there are some of the ammonium salts which does not give alkali. For example, ammonium nitrate, it is explosive in nature, it will not give alkali. Ammonium nitrate, it will also not give alkali. So it will also not give, sorry, ammonia gas, right? So these are the few examples which on heating does not give ammonia gas. See here nitrous oxide, here nitrogen gas they are giving, right? Now very simple, from metal nitrides, means you can prepare ammonia gas from metal nitrides, right? Ammonia can be obtained by the action of warm water on nitrides, right? On nitrides it can be obtained. See here, magnesium nitride, aluminum nitride, and warm water is being taken and ammonia gas is prepared. So this reaction is also very simple. Almost same type of experiment is done, how it is done here, right? But in this case, what we are doing, we are not tilting the round bottom flask because no water is being formed, no such heat problem is there that water will fall and break this container. No. So warm water is falling slowly and slowly on these nitrides, maybe magnesium, maybe aluminum nitride, and again formation of ammonia gas. This goes to another container and it can be dried by CaO and ammonia gas will be formed here, right? Clear. And later on that ammonia gas can be collected, it can be tested also. Means how ammonia gas can be tested, very simple. We will, for example, here I have drawn this rod also, right? We will bring a rod which is dipped in concentrated HCl. We will bring here and we will try to react ammonia gas with this, and there is formation of this NH4Cl, ammonium chloride formation will be there. That means white precipitates will be there on this glass rod. Clear. So this shows that the formation of the gas here is ammonia gas, right? So quicklime packing is for drying, so you can say this is a drying tower. Similarly here also drying tower is there, right? Okay. Preparation of aqueous ammonia, right? Almost same type of experiment we have done in this diagram. If you remember this diagram, just a minute, let it to be focused. Okay, this diagram, if you remember, right, we have done in HCl chapter also. Same process is there, right? Means this inverted funnel is being fixed here, right? Why we are fixing here this inverted funnel? So that back suction should not be like this, that water rises up in this tube and goes back, right? But so that water should not rises, funnel, a large area is being given here, right? Means large surface area we are giving so that back suction should not occur. If you remember, whenever you are buying 20 rupees juice or 30 rupees juice and you are drinking it with straw, right? So you try to blow air in it, right? Try to blow air in it, you will see that from that straw juice start coming outside. So to avoid that such kind of a back suction, they have taken a wide mouth funnel arrangement, right? Clear. So let's see the procedure. Water is taken in a container only in small portion of, and the mouth of funnel is just dipping in the water. They have not read, means very less part of funnel should be dipping in the water. As ammonia dissolved in water at higher rate than its production in the flask, means it is absorbing very fast, means it is dissolving here very fast. Means here, suppose, say in numbers, if we want to say that only 10 part of ammonia has been discovered, made or prepared, right? That 10 parts are coming, it will dissolve here very fastly, and other parts still not made properly, right? So there is a chance of back suction, there is a chance of that water can go backward, right? So to avoid that, it has been, this type of arrangement is being done, funnel arrangement. As a result, the rim of funnel loses its contact, means sometime it loses contact also, because production is less and dissolving is fast. Since ammonia produced push the water down, right, and the funnel come in contact with water again, right? Means there is certain rising of the water here, but the gas found backward, there will be pushing, right? There will be pushing of that water, means because there is a little bit gap over there. Why? Because production less, dissolving more, so in that time water rises up, but at that time again some gas comes and that pressurize the water, that pressurize water to go down, right? And immediately water falls back again, right? And ammonia dissolves in water without back suction. And you can say that for large dissolving, large surface area we have given, also a funnel we have given, if there will be a pipe here, then definitely back suction will occur and water can go back, and due to trickling of water backside, this flask may broke, right? Now we are moving towards the manufacturing of ammonia with the Haber's process, right? Here we will be taking two gases. For Haber process, I will be showing you reaction here, right? Very simple reaction. Clear. We will be taking nitrogen gas plus hydrogen gas, and we will be getting ammonia gas, NH3, right? This gas will be prepared. Understood? Right? Nitrogen, hydrogen. Now we are going to balance it. We will put 3 here and 2 here. So we can say that 1 volume of nitrogen plus 3 volumes of hydrogen, total 4 volume, will give how many volume of product? Only 2 volume. But remember this reaction is a reversible reaction. Clear? Means I want to tell you that means only 15% of these two gases will be changed to ammonia. Remember this. Again, I am speaking, only 15% of these two gases will be changing to ammonia, right? Reaction is exothermic. This reaction occur in almost 450 to 500 degrees Celsius, right? Iron as a catalyst, molybdenum as a promoter here, right? And reaction is absolutely reversible. That's why I am saying from 100, means if it is 100%, only 15% of ammonia will be formed. Understood? So I want to say that means the other gas will be wasted like this, means 85% of the gas will be wasting like this. So there will be recirculation of these gases is being done in the experiment, and again we will be bringing back and changing again 15% from that left 85%. Then again from that left we will be recirculating the left part, and again we are changing to that ammonia gas. So like this we can increase the yield of ammonia gas. Now I will be explaining directly through the diagram. See, very easily you will be understanding through the diagram. See, from one side liquid air means sorry, liquid nitrogen we will be taking. From where we will be taking? By fractional distillation, right? Yeah, liquefaction of air, right? And hydrogen we will be getting from Bosch process. Bosch process, you know that Bosch process you have done in ninth class. It is very easy topic, you can see in ICSE books easily. Now both the gases will meet in a compressor where we will create a pressure of around 250 atmospheres. I have not written here, but now I am writing 250 atm, right? So we need pressure also here, 250 atmospheric pressure. However, in most of the books it is written from 200 to 900 atmospheric pressure, but in reality we are maintaining pressure almost up to 250 atmospheres only, right? So see, both the gases are coming as they are compressed. Now they are coming to a chamber where finely divided catalyst as a iron is there, right? Okay, in this catalytic chamber pressure is still maintained to 250. See, written here 250, right? Then it is taken to a cooling chamber and liquid ammonia is being produced here. But remember this thing, this liquid ammonia is generated here and collected here, but many of the part of these two gases is been moving backward. Why they are moving backward? Because I already told you, only 15% will be changing into liquid ammonia, other will be again recirculated and again brought into a container where 450 to 500 degrees Celsius temperature is there and around 200 atmospheric pressure is there, right? And again recirculation of gases is done, and again from those some gases some part will be reacting and will be changing to liquid ammonia, and again it will be given backs if some part again not reacted and formed to change to ammonia, right? Now we will be moving towards this last part, right? What will be the favorable condition? Again I am saying 500 degrees Celsius, temperature 200, finely divided iron as a catalyst, and pressure will be 200 atmospheric, and traces of molybdenum or Al2O3 as a promoter, right? Recovery of ammonia, right? As I already explained you process, I already explained you how much volume you will be taking in the starting of the reaction. When I am writing in the copy, I have already explained you, so we will not be going here in this topic again, right? You try to read this topic from your books, Hannah, and here see that 15% which I am talking is already written here. One important question from the above, I am going to tell you that why promoter is being used. Promoter is used to increase the efficiency of the catalyst. Remember this thing, this is an important question, can be asked for 1 or 2 marks. Now I am moving towards another important part, means these gases. Nitrogen we have taken from the fractional distillation of air, hydrogen we have taken from the Bosch process. Bosch process, you already know that in ninth class we are preparing water gas, and we are removing carbon monoxide from that part, right? Carbon monoxide first converted to carbon dioxide, then from with the help of KOH we are converting it into K2CO3, and that is removed, and we are left with hydrogen. That is Bosch process, right? Clear? So these two gases should be pure, means no other impurities should be there, because if any other impurities like traces of sulfur, carbon monoxide, these type of substances will be there, then definitely catalyst get poisons, and you will not be getting ammonia as a product. So this is all about in this lecture. Thank you.